question and then pause the video and practice this on your own. If I give the question I'm going to ask is, what is the hybridization for each carbon below? So in one, I'm going to give you this molecule. Then I'm going to give you this molecule. And finally this molecule. So for every one of the carbons in each of these molecules, determine the hybridization. Okay, I hope you figured this out, or at least made a stab at it, even if you don't have the right answer. All we're going to do is count the number of domains around each atom. So for the carbon, we have 1, 2, 3, 4 domains. 4 domains corresponds to sp3 hybridization. For this carbon, we have 1, 2, 3 domains. 3 domains corresponds to sp2 hybridization. This carbon has 1, 2, 3 domains. Again, that's sp2 hybridization. And this carbon also is going to have 1, 2, 3 domains, sp2 hybridization. The carbon in CS2 is going to have 2 electron domains. That's going to be sp hybridization. The carbon in carbon monoxide has 2 domains. That's going to be sp hybridization as well. Now, the reason we build up this hybridization model is to explain not only the shape of the molecules that we observe in real life, or at least in the real life of our data, but also to explain orbital overlap of bonds in various molecules. One of the best examples that where this is necessary is if we look at the series of molecules C2H6, C2H4, and C2H2. In C2H6, the Lewis structure looks like this. And if we were to describe the hybridization on the carbon, that would be sp3, because there are 1, 2, 3 domains. So let's draw it like this. We'll have the carbon, we'll draw a C for the nucleus of carbon, and then we'll have our sp3 orbitals coming off of that carbon. The other carbon, we're going to have an sp orbital. Each of these are sp orbitals, sp3 orbitals. And each of these sp3 orbitals is going to overlap. These two will overlap here in the middle to form the bond that exists between the carbon atoms. And the others will overlap with 1s orbitals of H to form the bonds with the hydrogen atoms. So the bond between the carbons is due to overlap of 2 sp3 orbitals. The bonds with the H's are due to the overlap of hydrogen 1s and the carbon sp3 orbitals. Now for C2H4, this becomes a little more complicated. The Lewis dot, as will not surprise you, I'm sure, the Lewis dot structure for C2H4 looks like this. So we have a double bond, and this is where things get interesting. So we would say there are 1, 2, 3 orbitals, domains, around the carbon, and so this was going to be sp2 hybridization. So we're going to draw the carbon with 3 sp2 hybrid orbitals coming off of it. These over here will somewhat uninterestingly bond with 1s orbitals of hydrogen. The carbon in the middle, they will each have sp2 orbitals that overlap. So this is the first of our two bonds. Where does the other bond come in? Well, the other bond comes in from the unhybridized orbital of carbon. Remember, a carbon atom would have a 2s valence orbital, and it would have 3 2p orbitals. The third one coming out at you from the paper. So that unhybridized orbital, 3 of them are involved in making these sp2 hybrids. The other orbital remains unhybridized, and they occupy large regions of space above and below the plane of this molecule. And it turns out those unhybridized orbitals can overlap. And it is this overlap of the unhybridized p orbitals It's the overlap of these unhybridized p orbitals, this sort of sideways overlap, that results in the second bond. The first bond, which exists in between the nuclei, is known as a sigma bond. So this direct overlap of orbitals leads to what we call sigma bonds. Sigma bonds are always located directly in between the nuclei. The indirect overlap of unhybridized orbitals and it's always unhybridized p orbitals results in what are called pi bonds. So we would say that in C2H4 there is a sigma bond directly located between the two carbons as a result of the overlap of the hybrid sp2 orbitals, and then above and below the line between the carbons is a single pi bond. This pi bond, this region is a region where we would find the electrons, and in the second bond they may be up here, maybe both up here, maybe both up down here. One may be in each of these, but this is the region of space above and below the carbon where we would find the electrons. If you kind of try to draw this, you can imagine these sitting in one plane, and then above and below these carbons is the pi bond. So these two regions of space here are the second bond that in the Lewis structure are just drawn as a second line. But really they're completely different things. One of them exists in between and is the sigma bond. The other exists above and below the plane of the nuclei, and that's the pi bond. And my drawings are about to get even messier, so if we do C2H2, the Lewis structure looks like this. So we have a triple bond. Excuse me. This should have been, I'll start over. New paper. All right, so for C2H2, the Lewis structure would look like this. Each of the carbons is sp hybridized. So we would draw this with the sp orbital coming out each of the sp orbitals 180 degrees apart from each other. So we have orbital overlap here in the middle. That overlap in the middle there, that's our sigma bond. But now we have two unhybridized p orbitals. Again, going back to the carbon atom, you have an s and you have 3 p orbitals. These two combine to make the sp orbitals, but these two are unhybridized. So now we have an unhybridized orbital above the plane, and then another one so these will form a pi bond. And then you have another 2 orbitals, and these are coming in and out of the paper, and this is my old problem with trying to draw in 3 dimensions. You have another pi bond that exists in and above the plane. or excuse me, above and below the plane of the paper. So what you have is a p orbital. You have two p orbitals that are overlapping from the carbons in this direction in the plane of the molecule, and you have another pair of p orbitals that are overlapping above and below at 90 degrees to the region between the two carbons, forming a second pi bond. None of this shows up in the Lewis structure. In the Lewis structure, these look like equivalent bonds. It turns out they're not, and not only are they not equivalent in terms of energy, they're not equivalent in terms of their location. The sigma bond exists in between the two carbons, directly between the two carbons from the overlap of the sp orbitals, above and below the plane, and above and below the plane in the 90-degree direction, we have the overlap of a second pi bond, resulting from overlap of unhybridized p orbitals. One last example of this goes back to our friend benzene. So actually, let's do a quick practice question. How many sigma and pi bonds are in this molecule? And I'll give you just a couple of seconds. All right, so for this molecule, benzene, we have a total of 1, 2, 3, 4, 5, 6 sigma bonds. Excuse me, sigma bonds between carbons. Another 1, 2, 3, 4, 5, 6 sigma bonds between carbons and hydrogens. So carbon to carbon, there are 6 sigma bonds. Carbon to hydrogen, there's another 6. But each of these second bonds in here is actually a pi bond. So carbon to carbon, there are 3 pi bonds. So there's a total of 12 sigma bonds and 3 pi bonds in this molecule. The cool thing about it is that the carbons form sort of a flat hexagon, and I'm just going to draw it like a hexagon. If you can imagine that as a flat surface. And then the unhybridized p orbitals exist above and below that plane, and the electrons in those pi bonds just kind of float in between. So that there's a pi bonding region. If the molecule is flat, there's a pi bonding region above the molecule, pi bonding region below the molecule, and that is how we use hybrid orbitals to think about the molecule of benzene.